Hello everyone. We'll wait 1 more minute and then we'll start. Hello again. It's 5 o'clock Dublin time and we are ready to begin. Today we will be talking about trading simulation. Hopefully you all already know me. I'm a business intelligence analyst working at Google. I have computer science degree and finance and data analytics degrees, and I founded the pythoninvest.com project where I write about stock markets analytics. So here is the agenda for today. At first, we will answer for some questions from Slido, and I'll share comments from home assignment number 3. Then we'll talk about system design view, step number 4. We are quickly approaching the last step number 5, where we will have the automated trading system. The main part of our content today is modeling and simulations. So we will spend a lot of time on modeling just because we haven't covered all models and all approaches on the last time. And also it's a good thing for you to revise the content. In the modeling part, we will revise Decision Tree Classifier and Hyperparameters tuning. That was a home assignment task. Then we will cover 2 more models. One is random forest and another is neural network, an advanced model. And finally, we will introduce decision rules on higher thresholds of predicted probabilities. That is, you can artificially limit the usage of the model on some subset of the data when you know that the model predicts better. And next, after we are done with the modeling piece, we'll do simulations. And today we will cover only one simulation strategy. And this strategy will be to invest $100 in each positive prediction with trading fees. And that will be vector calculations, and we will generate new fields of predictions for each predictor, new fields of simulation. For you, there will be a task for a home assignment. You will slightly adjust the algorithm of simulation, and you will be asked to invest a higher amount of money, up to $150 per each positive prediction, depending on the probability of prediction. And on the next lecture, we will cover a more advanced simulation or more precise simulation, which will include reinvestment of capital gains, full usage of capital, risk management, entry-exit criteria, and portfolio optimization. So today we will have a simplified approach for simulations. It will give us approximate profitability. It is faster to calculate, and you can do it with vector operations, which is very efficient when you use Pandas. Let's talk again about system design view. On the first module, when we covered many data sources, we generated a set of files or tables where each file is supposed to be close to the original data source, and each file represents one data frame. On the second module, we generated one data frame from all files generated at module 1. We also created more categorical and numerical features and cleaned the data set. On module 3, we started from the first model, which was a Decision Tree Classifier. We then proceeded to the optimized module, Decision Tree Classifier with the Hyperparameters optimized. And today we will cover two more modules, Random Forest and Neural Network. And today, when we have all predictions, which are manual predictions, and all modeling predictions, we can use those predictions to simulate some trading strategy. And we will have a simple trading strategy. We won't combine any predictions. We won't use any shares or any advanced features. It will be just invest $100 in each positive prediction. As usual, you can add your questions at slido.com, #SMAZ. I didn't see many questions this time, but I'm reading it every single time. So let's start from homework number 3. And first, we will compare a number of responses and time spent for each homework, starting from homework 1, and then homework 2, and then homework 3. As you can see, the number of people who are responding is dropping approximately 50%. Hopefully, we will have some of you finishing all home assignments and finishing capstone projects. If we want to compare the time spent on homework, so we started from 2.5 to 6 hours for homework 1, then 5 to 12 hours for homework 2, and now it's 4 to 12 hours for homework 3. And as some of you wrote that you don't understand why there are these or those questions, I will give more details on the ideas behind the homework. So question number 1 was to generate dummies for months and week of months. The idea is simple, that you can use Pandas commands and you can create new categorical variables, which are usually quite important for seasonal factors, and they may serve a good source of new features for you. Second, define new hand rules on macro and technical indicators variables. The idea here was to replicate a few hand rules that I introduced during the lecture. They are very easy to generate with just one line of code, and the idea is that you can generate them with a simple rules of predictions. So you have at least 100 technical indicators. So if you want to generate some of predictors based on your previous experience, you can come up with so many hand rules. So our goal here is to understand later that modeling approach and using more advanced predictions is better for us in terms of profitability and in terms of time investment, so that you can target for less deals or less investments and with higher profitability than just simple hand rules. Next question was about unique correct predictions from 10 levels deep decision tree classifier. The idea here is that you may create many hand predictions or many models, ML model predictions with different hyperparameters settings, and these predictions can be used not only as predictions but also as new features. So every prediction can give a unique correct prediction or several predictions when only this prediction is correct. That's why you were supposed to find that the prediction number 5 gives only one incrementally correct prediction on a test set out of 30,000 examples. But still it is one prediction when only this model was correct. So if you use 10 models like this as additional features, you may increase overall quality of predictions. And the last point was about hyperparameters tuning for a decision tree. The idea here is that most of the ML models, they have some parameters which are called hyperparameters, and by default any ML model will be not very optimal, and you need to spend some time, and usually it is a computationally intensive task, to optimize those parameters. You need to define parameter space, what are the potential options for the parameters, and you'll need to combine all of the parameters from the parameter space and calculate the model, feed the model, and get the metrics that you target to optimize. There are some advanced methods of hyperparameters tuning like AutoML or gradient methods, and not just a grid search when you cover all possible parameter values, but we won't cover that in this course. Let's move to the selected comments and answers from home assignment number 3. I saw a lot of comments about growing complexity. This is true that all our previous modules and previous knowledge is stacking, and we need more and more experience, skills, and intuition to proceed towards our final strategy. So first, some of you mentioned that it's a very large data frame, but I can argue that I couldn't train a neural network, so I think that you can create even bigger data set, and it will be easier for you to train models and achieve better performance. The thing is that there is a trade-off, and you need a lot of compute power, and Colab by Google on a free tier doesn't give you this compute power. And then some of you said that it involves a lot of knowledge and skills about data science, advanced knowledge about Pandas and NumPy, that you haven't learned machine learning before, especially in time series. What I can say is that any model or hyperparameters tuning that is covered in this course can be easily a full book of studies, so it is hard to find one good pre-read or one good course, and my recommendation is just to replicate what you have here, read the documentation and links that I provide. Usually they are quite good, especially for Scikit-learn, and try to adjust this code and change small parameters. Don't really understand question 3 and question 4. Hopefully we've covered this already. Not familiar how to use get dummies. This is just Pandas question. Don't understand plot tree. We will cover this again. Plot tree and extract tree nodes, 2 different ways of visualization for decision tree classifiers. Then crash and collab every time. I see this problem too when you demand a lot of compute from a collab. When you run it for long hours, it can be crashing. It's not actually crashing, it's just not granting you enough compute, and it can be switching between different users so that the execution is slower, and you may need to wait until you are joined to the pooled set of users, and you have the resources again. Questions are hard and time consuming. Hints are not clear to understand. I try to provide more clear examples, direct steps, and some hints. But please, if you still see some confusion, ask questions on Slack, and I will try to answer them and improve the GitHub code. Content is getting extremely complex. There was one thing about the psychology of trading, so we are not using it directly, and I don't know how to formalize this. But my goal is to sleep well if I invest a lot of money with my algorithms, and that automated system can handle all of the potential problems automatically, so that I can monitor this system every day or every week, and I can shut down, or it can shut down automatically when something wrong is happening. So I don't want to involve psychology of trading in this experiment and in this exercise, but indirectly we see, of course, some of the features of like increased volume of trade around reporting dates. So you can extract some features, or you can notice some features that are covering the psychology of trading in the dataset already. So prerequisite trading and having trouble applying the code in real world. Right now we are in the experimentation phase. We're trying a lot of things, and on the next lecture we will have an MVP. So we will use only the best models that we trained already, only minimum amount of code in a separate files, Python files that you need to get the data, to download the data, to transform the data, to predict the model, or even use the saved model that you trained previously, and it will be easier to apply the whole system, which is currently spread it across several collabs in one small project or smaller project. Some of your answers to the missing data question. I think that you need to think about missing data and about important predictors all the time, and you need to design the system in such a way that you can easily add 1 or 10 new features and recalculate everything in 1 hour. So what you said, that we can include unemployment rate, industry-specific indexes, commodity prices, ratio of positive and negative news, market capitalization, technical indicators currently are using fixed time periods, but you can include look back for longer periods, not only last 7 to 14 days. I think that it's the default setting in a TLib, but last 30 days or last 5 days. So if you do the variation in time periods, you will have more features, bucket continuous features. So if you create a neural network or a regression model, it may be not as useful. But if you have decision trees or random forest, that's the main models that we have today, it can work well. So if you know, or if you debug your model, and if you know that it lacks the prediction quality for some specific days, and you know that during that days there was one of few factors which were extremely high or extremely low, you can help your model and you can create dummy variables which will be equal to 1 only for those specific days, like extremely high values of growth or unemployment rate or anything else. So it will be not a continuous variable, but a discrete variable or a dummy that characterizes a continuous variable. Volume of stocks after the first day of launch, then new feature types for constant growth, learn more about companies' financial results, like debt ratios, cash flow indicators, EBITDA, statistical model to extract seasonal trend. What I'd like to say that all of these suggestions are correct, and please experiment, and in your capstone project you will be rewarded if you add more features to the dataset. So now let's talk about time series modeling, and on top of the first executions of Decision Tree Classifier that we had previously, we will add optimization layer that is tuning hyperparameters and predicting probabilities and defining threshold rules on the predicted probabilities. We will also cover random forest, logistic regression, and neural network, but we will use for further simulations only random forest because it seems to be working well as a single decision tree. So first I want to show my example of a non-working tuning. So this is hard. You may not know why it's not working. Logistic regression, usually it's the first model of choice when you have a binary model or a classification model. And why is it the first model of choice? It is simple because it's linear on parameters. And we will see later today for a neural network, linear and non-linear, that linear networks, they are faster to predict, they are easier to interpret, they are efficient, so you can train them with fewer minutes. But sometimes it doesn't work. And as you can see here, I have several parameters, parameter values. So here there were two hyperparameters C, which is a regularization parameter, and max iterations, which could be 50, 100, 200. That's what I selected it to be. So I was searching on C and max iterations, and all of the results or all of the models, they delivered exactly the same precision score, 55.5%. And this is not a random number. It is an unconditional probability of success on a test dataset. That is, if you don't know anything, or if you don't use hand rules or ML rules and blindly invest in every single occasion for those 33 largest stocks in the last 4 years, you would end up earning in 55.5%. And you may know that last 4 years were bullish years. That is, they were growing very fast, and there were so many days when everything was growing. What was strange for me, that there was no improvement in the precision score. My guess of a potential reason is that there are too many features, 300 features, and I used 60 dummy variables which are not very informative, that we generated during homework, and maybe I need to use less features now to make it working. So there are only 125,000 records on a train and validation dataset. It is maybe only 500 records per each feature, and it may be not enough to train that many features. And one more addition is that Scikit-learn uses the numerical implementation of this model. That is, it makes several iterations, 50, 100, 200, and trying to improve parameters or adjust parameters, and to find the optimal target function. I didn't expect this. If you study statistics, there is a closed analytical solution, and you don't need to do these numerical calculations, and this can be a potential problem why in this case the model doesn't work, because it just can't start proper features tuning. And that was exactly the same reason why I couldn't finish neural network hyperparameters tuning. You can read this article about other reasons why your model is not tuned with different options for hyperparameters. There can be many reasons, but if you include more examples of hyperparameters tuning in your capstone project, even if they are not successful, you will also receive more points. In our case, I want to show the first code snippet, and it actually comes later after the more successful models, and it is commented here, so that if you uncomment it and run it, you may need to wait for 30 minutes just until it finishes. That's why I ran it once. I generated the precision matrix, and I recorded this precision matrix. So for every combination of C and a number of iterations, so here C equals to 1 and number of iterations, maximum iterations equals to 50, my precision score was 0.5551, and that was the results of a hyperparameters tuning. But feel free to uncomment and run it. And the thing is that if you use any models from the Scikit-learn, especially if these models are binary models, it can be a logistic regression, it can be a decision tree or random forest or some other models, the algorithm is exactly the same. So you initialize the model class. In this case, it's a logistic regression with some parameters, and I also chose a solver SAG. There are some other solvers, so maybe it's not working because I chose a wrong solver or something else. And then you feed the model on some set, and then you check the model performance on a test set on something that you never used before when you were doing the training of the model. And again, it's not the ideal way of doing things. Ideally, you need to feed only on train and check the hyperparameters on validation on a different set, and then when you select the top model on hyperparameters, you can use it for test. But in our case, I saw that it's not enough data to train many of the models that we cover here. That's why I had to combine train and validation set and sacrifice the purity of experiments on different sets. So let's move on to the next piece, and hopefully you got the same result when you were doing your homework. So here what I have. We train a decision tree model. We optimize on one hyperparameter, which is a maximum depth. So more depth, more cases are covered, and the model can explain more situations that happened previously. But there is a caveat that you can find a model of depth like 20 or 25 that will cover all potential options and that happened in the past on the trained dataset. But when you try the same model, a very complex model, on the test set, it may perform worse because it is overfitting, because it has so many cases, and it's trying to adjust its performance on the historical data. That's why you need to find a balance that the model is deep enough but not too deep, and the model should have good parameters. So let's see what we have here. We iterate over max depth, and the first value is max depth equals to 1, 2, 3, 5, and up to 20. And first 5 decision trees of depth between 1 and 5, they predict approximately the same stats, or they have approximately the same prediction quality of 55.5%. But after 3 depth 6, the model starts to learn. You can see that now we can predict 57% of correct classes, and then at some moments we can predict 58 or even almost 59% of classes. And after that time, when you increase further the maximum depth to 16, 17, and to 20, you start to overfit. So you will have the model that explains perfectly the train set, but not the test set. So now from this exercise, we memorize that you need to train the decision tree classifier of depth 15, and you train this model. You can predict on all train, validation, and test set. For trading, we need only test set, but if you want to define a column, and here it's called pred 6 underscore 6 underscore CLF underscore best, you need to have predictions on all data points so that you can join with the full data set of 2000K records. Code snippet number 2. So we define train, validation, and test set. We try to feed the decision tree. We again define the decision tree classifier object with the specific parameters, and here the only parameter that is different is depth. And then after the model is trained, you can predict on validation and test score. In homework, I wanted you to see that if you predict on a train and validation or just validation sets, you should see that the precision goes up. It looks like you're improving on the quality of the model. But if you predict on the test set and check the precision score on the test set, and the precision may not go up with the more complicated models. And again, in the homework exercises, I asked you to use export text command, which is a nice way of looking at the trained models in compact output. So that's I can see here that I started from maximum depth number 1, maximum depth number 2, 3, and I limited all my models output with maximum depth number 3. So if my actual tree was maximum depth 5, I showed here only top 3 layers of the tree, and then it said that, oh, it's a truncated branch of depth 2. And if you scroll down to the optimal tree, it is quite a complicated tree, because you may not be able to get this tree with hand predictions, because there are so many of them. So first we start on GDP potential, US growth less than 3% or more than 3%, then fast D, then growth Brent oil, then growth 365D, and then there is a branch or sub-branch of depth 3. Sometimes it can be sub-branch of depth 12. That means that you need to go on 12 more rules to get the final answer, whether you predict 0 or 1. And the tree can become very, very big, and we can show the whole tree here on the graph. So I want to highlight the 2 different options of tree visualization. First, 2 weeks ago we covered this option, plot tree, and this is a small tree of maximum depth equals to 1. We know that it's not the most efficient model, but for the sake of understanding, it's a good example. So we have tree of depth 2, but there are only two rules that can be used to make a prediction. So rule at the root node, that is level 0, it compares GDP potential, US year over year, less than 2.7% or more than 2.7%, and then if it's less, it goes to the left subtree. If it's more, it goes to the right subtree. And then we have 2 more nodes at the level 1. So in the left subtree, we compare fast D. In the right subtree, we compare a different parameter, growth WTI oil 30 days. And then after you did these 2 rules, you can come up with a prediction. So this leaf node, so you at the next level, at the level 2, you will have 4 leaf nodes, and they are called leaf nodes because they are final decision nodes. So that it says that this class is negative. If you finish in this leaf, the model, if you use it with the default settings, will predict a negative class. If you end up in leaf 2, it will say it is a positive class. But the real case is that in this leaf there are 136,000 of cases out of 150 cases of a original data set. And the model simplifies the things, and it says that it's a positive class, but it has some precision. It has 55% of correct answers. So I divided 75,000 of correct predictions of class 1 on total number of samples, 136,000, and I got this 55%. So if you end up in this leaf number 3, I have a different precision of 51%, but the model by default will say that it is a positive class as well. And leaf 4, it's a negative class. So we are interested more in the positive classes, and that's why our all scrutiny is to understand the performance of these leaf nodes. And for more complicated models, it can be many thousands of these leaf nodes. One more thing that I wanted to show here is that you can define a different decision rule, and we will use it later. You can say that I won't look at the default class labels, positive or negative, but I will look at the precision in each node, and I can say that if I create a decision rule with a precision more than 53%, that leaves only this node, and I can say that if I will end up in any other node, I can't get this precision of 53 or more %. So I need only this node. That's why the tree quality can be very different if you look at some subtrees or potential pulse or potential market conditions. That is, if you go left and right, this covers maybe 80% of cases, and for these 80% of cases, the tree performs better than for other 20% cases when it tries to predict a positive class. And on the right, there is another way of looking at the tree. It shows less information. It shows just the structure of the tree, that we have GDP potential yes year-over-year rule as a root. On the next layer we have FAST-D on the left subtree and growth WTI on the right subtree. So these are two equivalent representations of the tree, just the right representations is shorter. And now we can move to our best decision tree. And best decision tree, it has 15 levels. And when I show here this picture, I show only first two levels, or level 0, level 1, and level 2. And then from this picture on the right side, you can see that after these levels, there are big subtrees of depth 13. So in order to get the answer true or false, or for the potential growth, you need to ask up to 15 questions, and then you will be able to get this answer. And this tree has approximately 5,000 nodes. That's the number of nodes on the levels that are not leaves, that are not final predictions, and 2,500 leaf predictions. And you can think about these nodes as parameters. So you need to adjust this parameter. You need to find which metric you want to look at, what is the condition. So you need to train this model, and it is a lot of things to do if you want to train this decision tree of depth 15, and that's why it takes some time. In my example, I think it was about 6 minutes to train an optimal model of depth 15. Okay, now let's move to the second hyperparameters tuning exercise for random forest. So random forest, if you never worked with this model before, it has a similar interface. It's just a different class. It's called not a Decision Tree Classifier, it is a random forest classifier, but it has more parameters to optimize on. And first parameter is the maximum depth. That is the same, exactly the same parameter that we used to train one single tree. And second is number of estimators, or number of trees to estimate. The idea here is, and the number of estimators in my case could be 50, 100, 200, or 500. It's a many estimators, or many trees to train on. And the whole idea of this model is that you can train 500 very similar decision trees of maximum depth 15 or maximum depth 17, and then combine the predictions from those trees with some function like average prediction or average probability or some other combination, and the result in is prediction will be better in many senses. And it's a well-known fact that random forest it's better than a single decision tree because it reduces overfitting by averaging multiple trees. So we have estimators that is 50, 100, or even 500. And it improves accuracy and robustness to variations in the data. That's why, even though that I couldn't get 58% of precision score, but I knew that random forest is an aggregation of many individual decision trees, and I use this predictor in my final data set of predictions. And there are two more results here that lines with more estimators, 500 or 200, they tend to deliver slightly better precision score, so they are higher than red and blue lines with less estimators. And then they tend to show better training when I increase maximum depth. So maybe for this, for random forest, I should have tried not 15 to 20 maximum depth, but maybe 15 to 25 maximum depth. And that's one idea. Second idea, it may be a signal of overfitting, that it creates so complex trees that it slightly improves the score, but on the actual data, on the test data, or even on the real data, it won't perform really good. So for our predictions, I use a suboptimal model which shows 57.3% accuracy precision score, sorry, and it was 5 minutes to train. And I also commented this code snippet number 3. So if you run it again, you may need to spend 2 hours to get the same data that I received for this graph. That's why I pre-calculated precision metrics for each combinations of maximum depth and number of estimators, so that you see the results here and you can have all the details straight away. So you don't need to retrain it, but you can try on your local computer, and it may be much faster than just a 12 gigabytes RAM cloud call-up. So deep neural network. So this is the most advanced model, and but I still want to cover this. We will use a visual playground on tensorflow.org. I provided the code for hyperparameters tuning. You you can try to use this code. If you have more data and less features, it may work. But theoretically, this model, it's a connecting point between simple or standard statistical and econometrician models with deep neural networks and with more recent advancements. And why this model is the best one if you can train it properly. So it can reveal or capture complex patterns because it is a non-linear model. It can have many parameters, not just 3,000, 5,000. It can have 150,000 parameters if you have big enough data set. And it can predict nonlinear relationships. So let's check what we have on this playground. So for example, we have a simple problem with only two features, x1 and x2. And these features are between -6 and +6. So this is output. And there are some generated features like x1 square, x2 square, x1 multiplied on x2, sinus x1, sinus x2. It's very, very similar to what we did, and from two features now we have 7 features. And then there are different data relations or data types like this or like this, that you can easily see that you can draw 2 lines and it will work perfectly to predict when there is a class blue and when there is a class orange, and it will show the weights. So that's the parameters that we are training. So some weights are bigger than the others. It is training. It can train for a long time, but at some point after several epochs or iterations, it may not learn more, and it can still have some small set of wrongly classified features. But that's the process of training, and you can improve or make it more complex by adding more layers, like this, 3 layers, 5 to 4 and 2 neurons, and run it again, and it quickly trains on this. If you select this data set, it looks like non-linear, but it is linear on parameters. So it will find that the most important features are x1 square and x2 square, because we know that there is an analytical formula, x1 square plus x2 square, it equals to the circle, and these features are more bold. Finally, if we have a data set like this and use some linear model, you can see that it won't converge, so it doesn't predict anything. We don't have correct orange and blue classes, just because the pattern of data is very complicated and non-linear, that you can't separate it with strict with direct lines. But if you change the activation to ReLU, with what is called a non-linear feature of a neural network, it can learn, and it can learn relatively well, that it can predict for many of the cases the correct classes. So you can play with this with the learning rate, activation, regularization, number of neurons, number of hidden layers, and that's exactly what I did in Hyperparameters tuning code on Tensorflow, but I couldn't make it working just because it's not enough data, and it's too many features that we want to train on. Maybe if I select top 20 features from the most important features on the decision tree and run it again, and I can get even better results that I am getting on random forest and decision tree. So finally, we are moving to changing thresholds in a decision rule. So it's not a simulation yet, and simulation will be simpler than all of this complicated data science ML stuff. But this piece is equally important as you can train classic statistical models. And the idea is that we can use not just the classic predictions of classes of 0 or 1 from the decision tree classifier or random forest classifier, but we can manually redefine the decision rules and say that if the predicted probability is more than 50% or 55% or 60%, we will define only in that case a positive growth output. So we are artificially limiting the number of cases when our tree is predicting by betting on a higher probability events of a positive growth, or at least we are thinking if model works correctly and if it trained correctly, it should predict higher probability on growth days, and that's how we will create even more predictions on the same models. So here we have code snippet number 5, but before that let's assume that we ran our 30k of test predictions on an optimal decision tree model of maximum depth 15, and in each case we ended up in a leaf node, and that leaf node said that actually it's not class positive or negative, it has a probability of a correct or probability of a positive outcome which equals to 60% or 80% or 99%. And then if you plot a histogram distribution of these probabilities, you can see this picture, and this picture will be very different if you do it for a random forest or if you build it for another decision tree. So in simple terms, you use predict_proba method, and we have just 2 classes in a classification rule, so we do not extend it for a more advanced things when we can define classes of fast growth, small growth, high negative growth, etc. We have only positive growth and negative growth, 2 classes, and the model gives 2 predictions for each record. First prediction is for class 0 and second prediction is for class 1, and it says that 51% is the prediction for class 0 and 48.7%, so they have 100% in total, is the prediction for class 1. And here you can see that the distribution of predictions is like this. The average prediction is 52.6% probability, and median prediction is 58.3% probability. So this is close to the unconditional probability of a positive class of 55.5%. So the model gives an approximately correct distribution of predictions on a test set. Let's look at the code. So code snippet number 5. Here is what we do to get the predictions. Instead of predicting 0 and 1, we predict these pairs of probabilities for each observations for each record. But what we actually need, we need only second prediction, which is a prediction for class 1 or class optimal growth. And if you convert it to a data frame, it will be like this with 30,000 of predictions. When you have those 30,000 of predictions, you can plot the distribution of positive predictions, and then you can try to create more decision rules or new decision rules. And this is called true positive rate underscore for positive rate data frame function. You can spend more time later while you will be asked to do this for a random forest at your homework. But the idea is like this, that if the threshold is 0, that is for any prediction, even if it is 0, we blindly predict that it is a positive class. And it has true positive 16,000, false positive 13,000, and precision is 55.5. So that's we have the predictions, but we are not actually using them. The standard prediction at 0.5, that's what you get by default when you don't have the decision rule. That says if the probability of a prediction is more than 0.5, the model will say that it's a positive class. And for this positive class, the actual positive will be 11.6 K predictions, and false positive will be 8.2 K predictions. So the precision is higher, 58.6%. That's what we saw while we trained our optimal model. And now comes the tricky part, that if we increase the decision threshold, say we want to have more than 66% probability, the precision is slightly higher. It's 59.2%. But this may be enough to increase our quality of predictions and to increase the overall financial result, and to add more intuition that if you have less trades, you pay less fees, and if you try to bet more profitable trades, each individual trade on average will deliver you better results. And also, if you don't have an automation or a programming code that can place the trades automatically and you do it manually, you want to have less trades, and you want to trade not that often every day. In this case, you may need to trade 33 trades every single day, 5 days in a row, and it can be hours of your work. And in the end, it may not deliver profitable results. That's how you can calculate this function, this table, and you can reuse the code. And oftentimes, I look only at the thresholds between 0.5 and 0.8. It can be every even threshold or even lower granularity, and you can draw the graphs like threshold value between 0 and 1 and precision, and you can see that it is growing slowly, and at some moments of thresholds equals to 0.66, if I remember correctly, it has the optimal precision of 59.27, or actually 0.78 is 59.36. But these may be two rare events, and you may not have any examples of these events in the test set. So let's return back. we have just a few slides left, and they are quite important slides to get more predictions and to understand how we work with those predictions in simulations. So here we generate two more rules, and it's prediction 7, decision rule when probability is more than 66%, and prediction 8 when probability is more than 78%. And also I added columns with not only predictions, which are 0 and 1s, but probabilities, which is some number between 0 and 1, and it can be useful for you when you try to simulate. And for example, in the homework, you will be asked to have a slightly different trading strategy. You will be asked to invest slightly more when the predicted probability is higher. So it is a natural thing to do. When the model predicts that it's a higher probability of growth, let's invest more and see what financial result you can get. So let's look at the code snippet number 5 first. Code snippet number 5. We have those tables defined, and now we do exactly the same thing, but for a random forest classifier. So here we predicted, so first for a decision tree we have two rules, prediction 7, best rule more than 66%, and prediction 8 for a decision tree classifier, best rule more than 78%. And we just check how many predictions, if a prediction is more than 0.66 or more than 0.78, and define new columns in our data set. So it is two more predictors, and additionally there are columns proba prediction 7, which is a number between 0 and 1. The same idea is for a random forest classifier. It is it's a more complicated model of a maximum depth 17, number of estimators 200, and it gave us slightly less precision of 57%, but for if we increase the decision rule, and here it is 55% and 60%, you can play with these decision rules, and you can understand that if I used 66 or 78%, I wouldn't have any positive prediction. So it would be a too limiting decision rule, because a random forest classifier is a different model. It is a more generic model. That's how we have prediction number 9 and prediction number 10. So here is what we have on the predictions that are not manual, but predictions on models. We have prediction number 5, which is a default 10 levels deep decision tree. Prediction number 6, best decision tree of depth 15. Prediction 7, best decision tree with rule 66. 8, best decision tree with rule 78, and 2 more predictions on random forest. What is interesting here is that if you check those predictions on, say, test set, so they were not trained on this test set, and in each case there are about 30,000 records in test set, and these predictions, they perform very differently. Prediction number 5, it says that you need to invest in 25.6 thousand cases, like almost 80% of cases you need to invest, and you can get precision 56%. But prediction number 10, which is just a cherry picking prediction with a high decision rule, it says that you need to invest only in 695 cases out of 30k cases. So that's the idea, that we want to have less predictions, but we want to bet on more profitable predictions and pay less fees. And now let's move, or before we move to the simulations, there is a visual comparison of prediction number 10 and prediction number 9. So prediction number 10, it says that there were only 162 days out of 900 days or 4 trading years of test simulation where prediction number 10 showed any positive predictions, and oftentimes it was just 1 or 2 stocks out of 33 stocks when you were supposed to trade. But sometimes it said that you need to have 20 or 25 or even 30 predictions. Here it's 31 predictions that were positive. Say on average there were 4.3 cases, and mean is only 2 cases. The question for you is if we invest $100 in each positive prediction, what capital should we have to be able to fund this strategy? So let's say I need to have 30. I know that the strategy can have 31 positive predictions 5 days in a row. So you need to have 155. You may need to invest 155 times $100 each. So you need to have $15K dollars just to be able to invest with a small amount of money. And let's say that it's not very often, and we can simulate approximately. We can say that we won't be trading for these rare events, and we will trade only up to 6 positive predictions, and here up to 13 positive predictions. So we can disregard other positive predictions because we won't have money to do that if there are many positive predictions in a row in 5 days. So that's how you can see that's 2 predictors, predictor 10 and predictor 9. They are very different. Predictor 9, it shows on average 8 positive predictions a day when you need to trade, and predictor number 10, it shows 4.3 predictions a day, positive predictions. And for predictor number 10, you need just 2,000 capital. So just if you trade not more than 4 positive predictions a day, 5 days, it is 20 predictions multiplied by 100, it is 2,000. And for this predictor number 10, you need to have 4.5 thousand because it has more positive trades predicted. So actually it is 8.5 or 9 multiplied by 5 multiplied by 100. Okay, now, and this is the last part, and this is not very complicated part in terms of calculations. We have everything ready for simulations, and let's imagine that our strategy is to invest $100 in each positive prediction, but not more than 33 times per day if we choose prediction number 6, which has a very high number of positive predictions. So 75% quantile equals to 33 predictions. So oftentimes it says just invest in anything, in everything. And here are 5 random traits on prediction number 6 classifier. So it's a best decision tree. There was some date, ticker Microsoft, close price, and this is a predicted growth future 5 days. This is a positive growth future. It equals to 1 because in 5 days you can get 3.4% of growth, and predicted classifier value equals to 1. So in this case, you know that if you invest 100 and you get 3.4%, your gross revenue is $3.4. So this is the new column that you generate for a predictor number 6. And this column is simulation 1, first strategy, simple strategy, gross revenue for predictor number 6. We get $3.4. Then we assume that all trades are not free, and we pay 0.1% of fees for each trade. So it is 0.2% for buy and for sales for 2 trades, and on $100 approximate commission will be $0.2. And that's how you will end up with the net result, which is equal to $3.2. So this is the simulated financial result on a test data set when you used predictions from best decision tree classifier. Sometimes our predictions are not correct. For example, here on the second case, prediction was 1, so we predicted that it will grow. It didn't grow, but fortunately for us, the drop was very, very small, less than 0.1%, and we lost just 7 cents on this $100 operation, plus additionally fees of 20 cents, and the net financial result is minus 27 cents on this operation. So now you can imagine that we can generate this first, second, and third column with one line of code with vector operations on Pandas. And when you have this column generated, you can just summarize all of them on a test dataset on all cases of a positive prediction. So when model predicted us to trade, we traded, we got some gross revenue, sometimes positive, sometimes negative, and in total it was about 14.5 thousand over 4 years. Then there was about 4,000 of fees, and net revenue was 10.5 thousand. If you think about your approximate results, so we attempted to trade 19,000 times. That's a lot, and you can't do it manually. We earned 10.5 thousand, or approximately $0.53 per each trade of $100. Not a very rewarding thing, but it was only a 5 days trade, and it was 0.5% of a net revenue, which is not bad. Let's look at the code snippet number 7. So here is how you can simulate what you need to simulate in a few lines of code. We have a prediction number 6. We see that there are 30,000 of records in 947 days. We use a growth future 5-day actual growth in 5 days to calculate the result from the trading activity. And is positive growth 5-day future. We use this column to understand whether our prediction was correct or not. And here is the main part of a simulation. So gross revenue, it's simply you take the vector of predictions, and if you remember, our predictions are 0 or 1. So if you multiply vectors of 0 or 1s on any scalar number, say $100, you will have the resultant vector of hundreds or zeros. And then this vector of hundreds and zeros you multiply on the actual growth. So this actual growth that happened for each case, that is, you subtract 1 because you want to get the growth above $100, and that's actually $100 multiplied on percentage growth. Like if you had a growth of 3%, it will be $3 here. If the growth was minus 3%, you will have minus $3. So in the end, you have a gross revenue that equals to a vector of values, and this vector is 0 for all cases when prediction was 0, when we didn't trade, but it equals to actual financial result, positive or negative, when we traded for $100. In your case of a home assignment, you may need to adjust this 100, and you may need to have it 110 or 150 or 130, depending on the probability, and you will get a different financial result. Then if you know when you trade, that's actually all ones in the prediction, you know the fees that you pay, multiply 100 multiplied by 0.2%, and this vector will be minus 0.2 or minus 20 cents for each trade that you made. That's the approximate fees, and net revenue, you sum up gross revenue and fees, and you see the net revenue that you got, and you can approximately check that the growth was 3.4%, and you have here 3.4 gross revenue, or here gross future was 4.5%, and here you have $4.5 of a gross profit. So that's how we designed the simulation. And now we want to add slightly to add a few more metrics to be able to understand what's the end capital that we get, and what's the profitability of our trades. If you know the gross revenue of 14,500, that's what we got from trading, fees 0.2%, and but overall we had many trades, and it is 4,000. Net revenue is 10,500. Then we knew that in order to have enough capital to invest $100 for each positive trade, we need to have 16.5 thousand of capital. Otherwise, at some moment of time when we need to trade, we don't have capital. So that's the capital that we start, 16.5 thousand. And after 4 years of test simulations, we got 16.5 thousand plus 10.5 thousand net revenue. It is 27,000. This is a final capital. And the same example that we had in homework number 1, if you divide one on another, it will be approximately 50% growth in 4 years. This is not bad. And average compound annual growth rate which you can calculate with this formula, is 13.1%. And this is the most important metric that we have for any trading prediction and trading simulation. And this metric can be quite different from what you have in the precision metric or accuracy metric or any other modeling metrics. So we need to have simulations, we need to define the strategy that we are doing, and for this strategy we can also get an approximate profitability. Per each trade is $0.5, which is 0.5% out of $100. Average investments when we trade is 25. 75%, quantile investments is 33. So this is a very aggressive thing that it says you trade almost every day and a lot. And finally, you may want to compare it with some benchmark. For example, S&P 500 30 years growth was 10.8%. But we simulated our test trading over the last 4 years. So if you compare this S&P 500 growth over the last 5 years, which is very successful, bullish, yes, 3 or 4 out of 5 years, and overall CAGR was 14.2%. And now you see that we spent a lot of time designing trading and doing a lot of manual or automatic trading, and we could end up only with 13.1%. So maybe it's not good enough, and maybe you just leave everything with the passive investment strategy when you invest everything with the S&P 500 and you do nothing because you see this historical performance. So next, let's compare these results for different classifiers, and I selected very different predictions. Prediction number 6, it's a previous prediction. It had 19.8 thousand investments in test period, while prediction number 10, which is a very limiting prediction, it targets only a few deals, and it is only 695 cases. For 695 cases, we know that we need less capital to maintain this strategy. So if it predicts that we need to invest today, it because it predicts very rarely, it says usually it is not more than 4 to 6 stocks out of 33 to invest. That's why capital required is just 3,000. This is 6 multiplied by 5 days, it is 30 multiplied by 100. So that's if it goes mad and it says 5 days in a row that you need to invest in 6 investments per day, you will need to spend all 3,000 capital. In this case, what is different, that we have a modest gross revenue, 1,400, we have net revenue 1,200, but if you divide 1,200 on 3,000, so you will get 9% of CAGR growth with fewer investments. And fees are only 9% of gross revenue. So because we didn't have many trades, we managed to reduce our fees ratio, and we managed to use this properly. Say if you have 16.5 thousand of capital, you can just invest not 100, but you can invest 5 or 6 times more and utilize prediction 10 strategy to have these results. And finally, this is the last slide that I have for today. That's the comparison of all predictions based on the time spent. This is average investments per day. It can be 0, it can be 1, 2, 5, or up to 33 investments. And CAGR, that is compound average annual growth, maximum about 14%. And if you draw the lines of a passive investment benchmark, 30-year CAGR, that's a yellow line, about 10.8%, and 14%, this is a green line. For the last 5 years, you can see that only a few predictors are between these high growth rates lines, and most of the manual predictions, they are not delivering well. For example, manual CCI, if you remember, that was one technical indicator which happens not very often, but it has only 3.5% or less than 4% of a growth, of a predicted growth, or previous growth 1 day and S&P growth. So if you had a manual prediction here, you were supposed to do a lot of trades per day, like 22, but it still delivered only 4% of returns. So in our case, the general thoughts are modeling results are generally better than manual rules. And inside modeling, modeling with custom decision rules or betting on rare events works better. You see here it's best rule 55, best rule 60. Here CLF best, it performs relatively well as well without any custom decision rules, but it requires a lot of trading and you can't do it manually, you need to write automation. So for the next module, we want to write a better simulation so that it is not an approximate one, and that we will have to use iter_rows function and iterate row by row to write the exact prediction. And we need to do this just because we want to reinvest the capital gains. The main drawback of most of the predictions, simulated predictions for strategy 1 was that we didn't reinvest the capital gain. So we always had a starting capital like 10,000 or 15,000 or 3,000, and we used only that capital to bet only $100. But if we earned from 15,000 to 30,000, why do we still bet $100? We may want to bet $200 per each positive prediction, or we may want to invest or utilize the whole capital that we have on predictions, so that it will generate money for us and not wait until some rare events when prediction algorithms will say us to invest on many positive stock predictions in a few days. And we've also tried to introduce risk metrics and portfolio optimization. So to recap, today we spent some time discussing home assignment number 3, and then we chatted about hyperparameter tuning. We learned about new binary and classification models like logistic regression, random forest, and neural network. Then we found best decision tree models and best random forest models with non-customized decision rules. And then we tried to tune the the models and try to define a slightly higher thresholds for decision rules, and we came up with a higher precision, 59 and 68%. And finally, we discussed one simulation that is an approximate vector simulation of a financial result of one strategy based on all predictions that we had, and compared the financial result with the passive investment benchmark of investing into S&P 500. The homework number 4 will be published in a few days. I think it will have even less questions, maybe 3-4 questions and 1 extra exploratory questions. You will have 1.5 to 2 weeks to do the homework. Also, I will go on holidays in a few weeks, so I will try to publish the capstone project criteria so that you have you can start working on your capstone project before we have a module 5, so that you can have one additional week or so on working on your capstone projects. So one thing that I want to show here is the final code snippet. You can read through it, but the idea is that in a cycle I iterated over all predictions, and I generated exactly the same columns with a similar naming convention: gross revenue, fees, and net revenue, and then their numbers for the profitability of each prediction, and those numbers are stored now in a separate data frame, so that you can do any visualizations you want. And I will ask you to do the same simulation with a slightly different strategy. So you will be asked to generate sim2 underscore count investments, gross revenue, fees, etc. columns in a new data frame, and same columns in the existing data frame with individual predictions. That's everything for today. Thanks everyone for listening, and have great time learning new material. Thank you, and see you again.